We're going to finish this study of this case by briefly commenting on signal-to-noise ratio required by analog communication systems and also a little bit of information on human communication. If you consider different situations, here you have 5 typical analog signals we are familiar with. The first one is just our voice, and at the level that really we have filtered a lot the voice, and we just take from 500 to 2 kilohertz, 500 hertz to 2 kilohertz. This is more or less the bandwidth that will make our voice very intelligible. To distinguish this voice, to receive this voice, we normally need the signal-to-noise ratio from 5 to 10 dB. Otherwise, it will be impossible to hear and just follow this conversation. The following one is just the audio on the telephone system, on just the old plain telephone system, where a couple of wires really had a 4 kilohertz bandwidth assigned, and most of the filters and the signals sent through those wires really cover from 300 to 3.5 kilohertz. And that was typically the bandwidth for a phone channel, and to receive a good quality sound, we required something like between 25 and 35 dB of signal-to-noise ratio. If you try to broadcast audio on a medium wave radio, that's AM broadcasting, then the bandwidth is up to 5 kilohertz, and here you may need 40 to 50 dB of signal-to-noise ratio to get a good, let's say, quality, although 5 kilohertz really never made a very good sound, and that's why we had to go to FM radio. What was defined as hi-fi, high fidelity audio, which covers up to 20 kilohertz, then this requires signal-to-noise ratios of the order of 55 to 65 dB. And don't be surprised, this is more or less the order of magnitude of the signal-to-noise ratio we got for the FM station case. And then, finally, for analog TV, the one that we have just abandoned recently, for a PAL signal that had a video signal from 50 Hz to 5 MHz, the typical requirement was something between 45 and 55 dB just to get a very clean image. As soon as the signal-to-noise ratio began to deteriorate, then there were some kind of Argos points and some kind of white spots and image problems that really your eyes could immediately see. So those are the values for analog signals. One of the main reasons in moving to digital systems, besides the capacity of processing those signals, which is much higher than, and we are not compared with analog signals, is that they require much lower signal-to-noise ratio. So this is one of the reasons behind our move to digital systems. But now let me comment briefly on how humans communicate. And this will give us some information and some values to be related to the normal, let's say, radio systems we are familiar with. And I'm going to comment on how we see, how we hear, and how we talk. Our vision is really quite powerful. We, in our eyes, have about those numbers, could be changed. You can see different numbers, but the order of magnitude is correct. We have about 5 million cones in our retina, and they are the ones that deal with color and daylight. They work under daylight, they are sensitive to color. And they have pigments. In our retina, we have pigments that go up to more than 100 sensitive to different wavelengths. And we also have rods, and the number is at the order of 150 million rods. and they are needed to see under dim light conditions. And all those receivers are connected to about 1 million nerve fibers. So compare this with our electronic receivers, and this is really so amazingly complex that one cannot really compare them. We are sensitive to the optical part of the spectrum, roughly between 380 to 700 nanometers, and we are sensitive to different colors. That means we filter those wavelengths, and we have very clear reception of different colors. Our receivers are quite sensitive also. It's more or less estimated that 1 photon per rod and 10 excited rods will already produce a sensation of light. So we can see light with very powerful receivers on a very broad range of intensities, 10 to the 14, from dim light to a very sun situation where you are almost looking to the sun. But also our eyes could really be highly directive, and this is what normally described as acuity, which is how acute we are in sensing points. And this is more or less also the angle at which our eyes could see, could focus, and the number is 5 × 10⁻⁴ radians. That means that at a distance of 10 meters, with very good illumination, our eyes could distinguish points that are separated 5 millimeters. So we have a very powerful receiver for vision. And our vision allows us to write and read. And here you are going to find terms that are quite familiar to digital communications. For writing and reading, we use alphabets. Typical alphabet could be Latin, could be Greek, there are many Hebrew, there are many alphabets, but a normal alphabet we have about 64 symbols. And those symbols are combined in words, and we have codes for writing. We have grammar, we have understanding, we can understand different symbols, and we could work on them. There's also some other codes, like Braille codes for blind people, and there are also other ways of writing before the classical way we normally use. Could be shorthand. This is used by stenographs or tachygraphy, depending on what you want to do. And there are other codes we are very familiar with. One of them is the Morse code, which is just a code with dots and dashes. And we normally use also keyboards, and there you have a couple of them that are used. One is the QWERTY that is being used in all keyboards, but the stenotypists use different keyboards. So this is for writing and reading and our capacity to do this. If we go to hearing, things are a little bit different, but more or less the big numbers are similar. In our cochlea, we have about 15,000 cilia, hair cells, and they are connected to about 30,000 nerve fibers. And more or less, they can work in the frequency range up to 20,000 hertz. Normally, it could be 15,000. As you get old, then that number keeps decreasing, and also the low range increases. But the sensitivity of the ear is also astonishing. It's 10 to the minus 12 watts per square meter. This is lower than what we saw before in the radio. And also, this is sensitive, is just the response to very small pressure difference in our tympanic membrane. This is about 20 micropascals. Okay? The atmospheric pressure is 100,000 pascals. So look, this is really quite small compared to those values. The threshold of pain, which is the maximum power that our ear could more or less support, is 1 watt per square meter or 20 pascals. If you go above this level, then maybe your ear will break. And then the dynamic range for our hearing is 10 to the 12, from the minimum threshold to the pain threshold. And our ear responds in a log way, it's a logarithm receiver, and more or less it has a range of 120 dBs. But our brain is quite powerful too in other purposes. One, it could lock in to a source of sound to a conversation in a noise environment. You could be in a group, there's noise around you, but you can still hear the conversation nearby. It's a cocktail party phenomenon is well described. To do this, your brain could apply a processing gain of up to 15 dBs to this conversation and will follow it. If you lose it, maybe it will get hard to just to pick it up again, but it could really do this in a very efficient way. But also, we can sense difference in time of the order of a millisecond. And we use this for different purposes. One, the brain could also combine echoes of the same sound up to a certain delay and in some way to get a clean signal. But also, it could also sense with the 2 ears time differences between us phase and group, and this helps us to locate the sound origin, where the sound comes from. And also, we could also sense difference in amplitude from one ear to the other, and this has also helped to locate sounds. So really, we combine quite powerful measures to distinguish sound and the direction of arrival of the sound. This is just something to remember when we deal with systems. And just as a final comment, when we talk about voice, then here also we normally produce a fairly uniform spectrum up to 3 kHz with our vocal cords. Most of the energy is below 1 kHz, and most of the articulation, what makes us clear, is below 3 kHz. Depending on the voice, also we can produce fundamental frequencies of up to 400 Hz and all the harmonics needed. And this is more or less the basic parameters. We can produce sounds in 2 different ways. One is by having the vocal cords vibrating, and in this case we say that those sounds are voiced. Or the cords could be apart, and then we produce the sound with our oral cavity. In this case we say that the sounds are voiceless, and our sounds really is a nice mixture of those two. The vocal tones produced by the vocal cords and which are pumped by our lungs is really fed to a very complex cavity, our pharynx, the nose, the mouth. It's very hard to model, but some basic parameters, some fundamental parameters as the fundamental frequency and some small other information could be really get from a simple model. And we could model the oral cavity as a 17 centimeter long cavity that is closed at the vocal cords and open at the mouth and nose. And with this, we can really go a long way in representing those sounds and how we generate them. So with this, to finish this part, I just wanted to give you some flair of how powerful our sensors, our receiving, ear, and images, our capacity to deal with sounds and images, and how to compare this with what we are familiar with in telecom systems. And just to finish, this is just a page to acknowledge the authors of this material, the people that help us in preparing them, and the recording of this session.